Okay, Julie, thank you so much. Listening to Tony and Dan and Jim, and considering this is the beginning of the school year, I realize how much I miss this stuff. And I realize that, if I look back over my career, the reason why I got into academics, I really pursued graduate work, both my master's and PhD, were because of moments like this. I was a young student. I went to the Citadel as a military school. I remember we had special guests coming down. I didn't know a lot about the geotechnical profession, but I heard a few talks, and what I quickly learned that resonated with me was reflected in the comments that you heard this morning. I realized that as a civil engineer, there's something special about the field of geotechnical engineering. And that appealed to me. And that is, you have to be comfortable for working with large uncertainties. And you also have the opportunity to really be innovative and creative, because the solutions are highly variable. They're different every job, and the consequences of failure are high. And that's really what was reflected as I was listening to Tony's first brief introduction. He talked about the immediate issue with landslides here and the mitigation of landslides, about $235 million we know to repair the existing landslides. And if we look at the level of rainfall that we have, and remember, water is always an issue with most geotechnical failures. That's one of the key things that you had. So I can tell you a lot of the issues that we have with landslides here are associated with water. Some of that is associated with changes in our climate and much more water to saturate the hillsides and recharge those hillsides. But what you heard is we have a $235 million project in the region, and we have a budget that's $35 million, which is only 12%. We're used to being creative and innovative to figure out how do we identify the areas of highest risk, and perhaps we figure out ways to stabilize those landslides in some non-traditional ways. So if you want to be innovative, I quickly discovered geotechnical engineering is the way to do that. When Dan presented his talk about the geology of the region and how that's related to some of the current landsliding, it was a great discussion of how we find ourselves in an environment where we have, he showed an example where water was emerging in an unexpected place, emerging from the slope, which would normally be expected to be dry. But you find that there are regional differences and regional variabilities. You might remember he showed the instrument box that was flooded with water. One of the things I learned about geotechnical engineering is that your observation powers have to be on point. You have to look around. He noticed that that is something unexpected, and it's not a small issue. When you see something like that, there's a reason that's happening, and there's a reason that is related to some other deeper mechanism that goes against the theory, goes against what you thought, but it absolutely is something that you pay attention to, and you ask yourself, why is this happening? Because that's generally related to some other unexpected failure mechanism in the area. So having these observations and looking at what's happening and seeing things that you unexpect are really important. And Jim talked about how much the unexpected and completely avoidable landslide failures at the Killbuck site. The Killbuck slide was the landslide he talked about. He talked about how a poor site investigation and poor analysis and human factors related to failures there. It also shows how conditions don't translate from one end of a project to another end of a project. Although that site wasn't very far away, the results were very different. And so if you put all those together, there are two or three common threads that are related to all of geotechnical engineering. And that is, most geotechnical engineering projects have very large consequences, perhaps larger than any other field of civil engineering. We also, again, have to really be comfortable for working with large uncertainties, and we have to be innovative, and we have to be observant to really do our job well. So I've got just a few things that I want to summarize, but that's a summary of how I listened to the talk, and it reminded me as a student how I got really intrigued about this area, and went on to have a long career at Virginia Tech. So I was a graduate student at Virginia Tech, did a master's and a PhD. My PhD related to earthquake engineering because most of my advisors had recently relocated from Berkeley and Stanford to the East Coast. And you might not think of earthquakes being associated with the East and Central U.S., but some of the largest historical earthquakes and certainly prehistoric earthquakes have been east of the Mississippi. And I've worked all over the world on foundation projects, tunneling projects, big projects that are associated with earthquakes, especially along the waterfront areas. I'm going to show you a list of those types of projects. I've worked in soil improvement. That is, if you do have a slope that's unstable or a foundation and it's unstable, how do you make it stronger? And you do that cost effectively. And the tie-in with earthquakes is that most areas where you have large earthquakes, whether it's California, Japan, the central United States, the eastern United States, regions such as Turkey, the Mediterranean area. I've worked in places like Nepal, South America. All those are big earthquake areas. The damages from earthquakes, remember, earthquake waves travel through the ground, and the damage from earthquakes are really strongly correlated to soil conditions. And so typically, you want to talk about uncertainties. We have enough uncertainties from location to location in any soil mass, but now you add dynamic conditions. And so now you're figuring out what happens when you have earthquakes. And we certainly see soils, the sites that are underlain by poor soil conditions have greater damage and much higher mechanisms for shaking. I've got some of the coolest slides that you'll ever see from projects all over the world with some videos that show what's happening, three-dimensional waves and things like that I wish I could show you for some of the analysis of dams and nuclear power plants and big tunnels and ports and projects that I've just worked on that are fascinating throughout my career. I wanted to just finish up really to give you some inspiration of what geotechnical engineering is from my standpoint and why this field is important. We just saw landslides as a great example of us as civil engineers really adding value to society to help mitigate those particular threats. But geotechnical engineering is really cool because I guess one expression that I use is all soils are gray. All soils are gray, which means that you have to, again, be very comfortable working in gray areas. If we look at structural engineering, your level of uncertainty in structural engineering, most structural engineering examples are much, much lower. You might have uncertainties in load from wind or earthquake or whatever, but your structural properties are pretty much known. I mean, if you look at the modulus of steel, we know it's 29,000 PSI. We know what that is. We know what the strength of concrete, the stiffness of concrete is. What I'm saying is, if we look at soil, not only do we have the certainty of products that are manufactured with fairly tight restraints on the uncertainty, soil conditions are different all over any given site. They're different from location to location. They're also different with time. I mean, all geotechnical engineering really is the using of soil as an engineering material. So a geologist is primarily concerned with explaining how things are, how things got to where they are. Why is the earth like it is? Why are these soil deposits here? How did they get there? How did they behave? What is the mechanism? As a geotechnical engineer, our job is to use soil, basically, soil materials, which, you know, it's a broad definition of what that can mean, but to use soil materials, earth materials, as a construction material. So we're interested in how stiff it is, how strong it is, and how easy water flows through it, its permeability. Those things are always changing, and they're changing over time. And so all the three presentations you just heard all talked about water, all talked about changes in conditions of water. Water typically makes soil less strong. It typically makes it more compressible. And as we have increased rainfall, we have climate change, we have all these conditions that are changing. We have building and development going on next to it, which changes what happens during our original design assumptions. There's so many uncertainties that we have with it. We have to really be creative and innovative. And to me, that is what the challenge is. I remember both Dan and Tony talked about uncertainty. We talked about how much uncertainty there is about how much water is in the slope. We talked about what the strength is for a root mass, which is how do you know what that is? What is the level of uncertainty, and figure out a root mass? I think Dan talked about bringing out a come along and estimating the tensile strength that you get. All that is very, very difficult to do, very challenging. And that's what makes geotechnical engineering different than other types of engineering, which means we have opportunities to be more creative and provide more value to our clients than most other engineers in that way. And what I mean is, how do we account, when you have large uncertainties, how do you account for that? You use large factors of safety. You use large error distribution diagrams. And so what you start to be able to figure out is, if you're able to identify the key mechanisms of failure and reduce that uncertainty, sometimes it's through site investigation. So spending a little bit more, in the example that Jim just mentioned, spending a little bit more to recognize those Pleistocene sediments, spending a little bit more on site investigation could have prevented this whole slide and all of this mechanisms at the Killbuck site, just to reduce the level of uncertainty. So we use these large factors of safety, but we also have so many opportunities to add value. If we know that, for instance, our project is not going to be so sensitive to, say, compression under static conditions or water conditions, we can reduce those factors of safety in very creative ways. Or if you are a contractor doing soil improvement, most of the time you have a performance specification, which means instead of somebody telling you how you get the soil to a certain strength, it's up to you to get the soil to a certain strength or a certain stiffness or foundations. And you see amazingly creative solutions. So it's an area where we still don't have to rely so much on prescriptive codes for every single way we approach our solutions. We can be very, very creative in doing that. I think the other thing is the field is more multidisciplinary than most other examples, at least in most of my engineering practice, than other types of civil engineering. What I mean by multidisciplinary is geotechnical engineering naturally involves engineering, geology, math, physics, chemistry, mechanics, and deformations, hydrology, and it involves a lot of intuition and observation. But you find yourself working with geologists, you find yourself working with other engineers, you find yourself working with professionals that are in areas that are related to chemistry or related to paleontology or related to archaeology. I've done all those things in my career, which is really deeply satisfying. Even though I am when I was at Virginia Tech, where most of my career was, as a geotechnical earthquake engineer who worked on foundations and lots of other projects, I also was an adjunct professor in geology in the geophysics area, because lots of what I did was looking at geophysics, that is the movement of different kinds of waves throughout the earth to figure out and back calculate, determine what's in the earth, or determine how earthquake waves or other types of seismic waves generated either naturally or through instrumentation are going to behave during some event. And so I spent a lot of time in geophysics. That's what I mean by multidisciplinary. I've talked about how important intuition and observation is really important. But I also want to say, why is this field should be of increasing interest? Well, as I mentioned, all structures are in or on the ground. You can't name a structure that doesn't have to have a geotechnical investigation. Every single structure relates to every civil structure. Everything in the ground, on the ground, even if you go to the moon. One of my mentors was one of the original geotechnical engineers, Jim Mitchell, from the University of California at Berkeley, who was one of the geotechnical engineers during the Apollo flight, because they had to design the footpaths for the lunar module to land safely. We also they had geotechnical tools on the moon doing strength of those materials. We had to know how those materials behave. If you want to put in an offshore oil rig that's floating in the ocean, the challenge is, how do you anchor this thing to the seafloor? How do you do tests for a seabed that's a mile deep? How do you develop the technology to get the anchors in and certify they're in? If you're going to put in a deep bridge, how do you get those foundations in place and build in deep water? How do you build these tunnels through these areas? So all of these things are important. The other reason why this is growing is that we're running out of great sites. Most of the good ground, the areas where the rocks are, the soil is strong, we've got good bedrock close to the ground surface. Most of those sites are taken up. The area is developed in most areas. So now we have increase in density in urban areas all around the world that provides a tremendous challenge to groundwater, to the safety and stability of buildings. But we're seeing ourselves building in areas now where we've got more high intensity storms that are increasing in frequency with more water in the soil than ever. And we find ourselves building in marginal conditions and having to use more and more technology. So it is certainly a field that is of increasing importance because of the increase in challenge for all our structures. And again, you can't get away from it. A geotechnical failure is typically something that has tremendous impacts for all the structures, which means geotechnical engineers get sued a lot because of all the uncertainty and because of the consequence of failure. If you have a geotechnical failure, everything stops when you have a geotechnical failure. That typically is the largest, most significant failure. Imagine an earth dam that you build, a big, huge 200 or 300 foot high earth dam that retains huge reservoirs. You have overtopping of a dam or something. Imagine the loss of life and the loss of property. That's a geotechnical project I've worked on a lot. Huge slope stability issue, huge issues with earthquakes, with large earth dams, which we have a lot in the East Coast and all around this country. Many of them are very vulnerable. Those are the types of projects you really have to be on your game because the consequences of failure is really high. The last thing I will say here is just a few of the projects that I've worked on before I got here to the University of Pittsburgh. I've not only been a researcher all my career and worked on projects literally all over the world, I have also been a very active consultant on engineering projects all over the world. So this is a quick list of the projects that I served as a consultant on most of these, but also as a researcher on some of these. But just some of the things I was involved with sort of shortly before I arrived at Pittsburgh, and in my current role, I'm not able to do much of the fun stuff anymore. But I was involved with the earthquakes in New Zealand, and also I worked on earthquake design for the U.S. embassies in Nepal and Ecuador. Both of those have strong earthquake environments, very difficult geotechnical conditions, very soft soils. A number of projects along the waterfront in San Francisco related to earthquake. Charleston, South Carolina, I'm originally from South Carolina. That's an area where I did my dissertation, large historical earthquakes. In this case, I worked on some tunneling projects underneath Charleston, very soft clays, very challenging, and also the large bridge that goes from Charleston over to Mount Pleasant, if you're familiar with that region, the Ravenel Bridge. So the challenge is, how do you build the foundation for that large bridge structure, and what's the earthquake safety for that? I sat on the consultant board and worked on those projects down there. I was also led an investigation to Japan shortly after the major earthquakes that were there in 2011, and follow up after that. Huge tsunami, 18,000 people were killed in Japan. I worked on waterfront structures, the major ports along the waterfront from Tokyo north to Sendai, ports, airports, nuclear power plants. I was in Fukushima, nuclear power plant blew up, and I was there after that, and did a lot of studies and worked a lot with the Japanese about how to have better design and figure out what happened. And that was a project that's really still ongoing. It was a tremendous, it made a tremendous difference to Japan. And one thing I will say is, because of that event and because of the tsunamis, which took out nuclear power plant at Fukushima, which led to the lack of use of nuclear power in Japan, a very diminished use. Now, they've gone back in those same vulnerable areas and put liquefied natural gas terminals there. And they're still extremely vulnerable. The next tsunami comes in, it's going to wipe out those terminals. Japan is a country, just like it was in World War II, that has to import most of its energy. That's why they were using nuclear power plants. So the decision, because of earthquakes and because of a lack of foresight with these tsunamis and putting generators in the basement that flooded very quickly, that couldn't supply the electricity for the cooling system in the nuclear power plants, that chain of event led to Japan greatly reducing its nuclear power usage and relying more now on imported LNG energy from British Columbia and other places, which means they're more vulnerable than ever. And so these are the unintended consequences. I worked as a special project on Turkey, which is rapidly developing now as a strong economy. There were large dams down in the southeastern part of Turkey, right on very active earthquake areas, very close to the border of Iraq. We had to have armed guards to go out to the site, but I was the lead consultant for the seismic analysis there. We worked on the drought monitoring system for the island of St. Lucia, the nation of St. Lucia. I worked on LNG, large terminals, also for Mexico, for a site that was actually owned by Japanese, but it's in Baja, Mexico, very earthquake-prone region there as well. We had to actually design the safety of those facilities, and we had to look at the sloshing of the LNG liquid inside the tanks. And to make sure that stability of these LNG tanks were appropriate, and that the site was a good site. It's a very important site for North America, because this LNG terminal is where lots of energy from Texas, Mexico is exported, some of it to the United States, some of it exported out of the United States through Texas to places like Japan. Romania, I worked on real-time landslide monitoring projects throughout Romania, as well as some windmill foundations to generate electric power throughout that country. I worked on foundations in Egypt, and in this case we worked on geothermal foundations where we use the pile elements as geothermal heat sinks to cool the structures, much as a geothermal heat pump uses the stability of, typically the earth is 57 degrees or so once we get down into the ground, and we use that to either in the winter, draw some of that warmer fluid up from the pipes that we circulate through to cool our home with our geothermal heat pumps, and of course dump some of the heat in the ground and take advantage of cooler temperatures through fluid in the summer. So geothermal heat pumps, we designed the system where we use foundation elements with integrated loops, and I did that in Egypt. I led the investigation for the earthquake that occurred in 2011 on the East Coast and damaged the Washington Monument. So I was part of the investigation that figured out what happened in the Washington Monument, why it was damaged, what are the mechanisms of behavior, and how that should be repaired. So we were there at the monument doing that. And as Julie introduced me, most of this work, especially with earthquake work, is going into building code development for the central and eastern United States. So that's a quick tour of, wish I had time to show slides and all. My point is, this is a field that for me, has provided a lifetime of incredible experiences, the ability to be creative, and the ability to really exercise this ability to take complicated systems that are different everywhere, use tools, modern engineering tools, and probability, and tools like experience of looking at what's happened before, integrating all that together and being incredibly creative. There are very few fields that you can do that. So it's been rich. The only thing is I wish I had more time to do this fun stuff. In my current position, it doesn't allow me to do that. But thank you for allowing me to share some of my passion for this. And I want to also congratulate the community, congratulate Julie for her organization, and certainly Tony and Dan and Jim for all of their experience, and certainly the way that this community has come together to honor our rich legacy in geotechnical engineering and civil engineering in general. So once again, thanks a lot. And Julie, I'm indebted for being invited.
This point in the year that was extremely busy for you, we really appreciate it. And thank you everybody for hanging on. We look forward to seeing you next week. Again, this landslide seminar series will continue for the next 2 weeks, and we'll look forward to seeing you again. Thank you, everybody.